Hello? 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 Okay. So let me make this thing a bit bigger. So I just want to format text. No. Where do I get the font? Okay. Yeah, I just want to do a bit of a plug for getting students. Okay. So this is kind of generally my research area. Okay. Broadly, the theme is application of logic and logic-based analytical methods, okay, for analysis of software and recently AI system design and development. So of the last few years, I've been looking at AI systems, but I call it AI system, but I'm mostly looking only at deep neural networks. But I'm interested in extending that to machine learning in general, and there is this whole area of AI safety, and that is also interesting. But the emphasis is on using logic and logic-based methods, okay? So that you can give some kind of guaranteed assurance, yeah? So that's been an area. So traditionally, I've been working only in traditional software and hardware. I've done a lot of hardware verification also. I'm still interested in that, and there are lots of industry folks that are interested in that as well. But most of the research these days is in software and software safety analysis as well as synthesis. Okay, so tools, techniques to scale, formal verification. So this area of applying logic-based methods is usually called formal verification. Come on, yeah. To industry scale designs and code. There's a lot of work. This area started, in late 60s and during 70s, 80s. Certainly, there was a lot of, it was a very active theoretical research area. Starting 90s and so on, so they started moving into industrial practice. And these days, the most of the somewhat applied research is in developing tools and techniques to scale these things in such a way that the soundness is guaranteed. And even though these are undecidable problems in general, therefore you can't expect to get full completeness, but when you develop a certain methods, kind of have a characterization of the class of problems for which it works, okay, and it is complete. That's how this thing is done. So, and software synthesis, and you've already seen, in order to do these kinds of verification, you need to come up with invariants when you have loops and so on. So you did some exercises on your assignment. But they are very hard to come by. I mean, to automatically synthesize. How do you synthesize them? There's a lot of research there. And one approach is to, rather than having the human being write the whole thing, which one can always do, and you can see it's very tricky and it's quite challenging. One can come up with certain approximate or use machine learning. I mean, machine learning has also been used, various syntax guided methods. There's a whole range of things to come up with approximate invariants, and machine learning are good at coming with this approximate invariants. And then you massage them to make them precise, okay, and then correct, sound, so that they are real invariants. There's a lot of work there, and that's also an area that I'm interested in. And then the other kind of different area is distributed system analysis and verification. Applying these things to concurrent systems, and especially distributed systems, is quite challenging. And it's also the value there is quite high, because debugging these systems in a way so that the error is reproducible is very hard, and therefore traditional tools like simulation, etc., they fall short. Okay, and therefore there is a need for these invention there. Formula verification, distributed protocols, and all these methods, even if you don't, when you don't want to do it, you develop proofs. I mean, that's also an area, and then develop tools like verification tools. You can also use those concepts to develop testing methods. Okay, I mean, testing methods for all of these things are random testing. Okay, that's what the industry uses. But random testing, but it doesn't give you real coverage. Okay, if you're able to do proofs in these things, you know that you have verified it for 100%, at least for the properties that you're able to verify. So can you use these kind of concepts that you do, like invariance and so on, to combine them with randomized testing methods with that can give you coverage assurance? Okay, in some sense of coverage. In some cases, it will be a combination of some state coverage and so on, combined with some probabilistic coverage as well. So, and then one application area specifically that I'm using both for doing proofs as well as thing is because distributed systems, they are various protocols are used in blockchain, the infrastructure for blockchain. So that is one specific application area that I'm concentrating on. So I'm giving a very general thing. So if any of you are interested in pursuing either masters or more advanced in these areas, related areas, I know that I don't know how many of you plan to do your higher studies, continue to do it here. But be aware, and you can spread the word around anything. And of course, the final area is what this course was kind of about. And this is the third time that I'm offering this course, and I've kind of fine-tuned it to the point where I'm actually doing some projects that are of significant thing. And that is generally I call as AI safety, but I haven't approached there right now. I'm concentrating on the safety and robustness properties of deep neural networks. Even within deep neural networks, I'm interested in these two properties of explainability and interpretability, which I haven't looked at. And the community is apparently quite interested in shedding light on what exactly those things are and whether you can come up with some analysis methods and so on. So that is something that I normally do. I mean, I've been wanting to create a website for myself, which I don't have an official website on which I will put some projects, okay, which I still plan to do. And please, when I do that, I will advertise, and you can visit that. Okay. Okay, so next, what did I want to show? I know what I wanted to show. This is the intro thing. Yes, this is what I want to be sure. So the coursework and grade distribution, this is what I had in the first class that I showed you this. I'm going to stick to this, and I hope it's okay if you want. So there will be this quiz, and the quiz itself is, I'm thinking of doing it, distributing the weightage in terms of the problems, okay? Now, I don't know how far I'll get to this DPLL-T today, okay? Usually I underestimate the time that I don't. If I'm hoping that I can get it, I do get it. Most of what I'm going to test you will be whether you've understood the concepts, because it's take home. It will be something where I will give you some problems, actually working on some examples where you will apply those concepts into the thing. It will not be where I'll ask you to do some proofs of correctness and so on. So be more illustrative, just to test you that you got the understood the concepts and then you work on it. So that is the thing. But there's one change. I haven't gotten around to making the exam, okay, and I have to leave to attend to some family commitments that thing, and therefore I'm not sure, and I'll only come back on the 29th. And I don't think between now and tomorrow I want to put most of the time in grading your assignment too, so that you will get it back and you'll have an idea of how much you've had, and so you can plan for the thing. I mean, as I said, 40% is for projects. If you do good on that, you should be okay. But whatever fine variations that you get will be, how well you do on the other things. Yeah. So we had tentatively, I had proposed 29th to get out on 29th and on 30th. How about if I pushed it to the thing? So I will give you a couple of days before everyone gets back if you're traveling. So do it on, say, depending upon when is the earliest that you get. So maybe December 1st, if I give it out and get it back, you can submit on December 2nd. Is that okay during that week? Yeah, you tell me, when is the earliest that so you see, we have that entire week, because after all you will have to do. So I can do two, you can go out on 2nd and you can give it on 3rd. How about you? No, you don't know, you don't remember. They're two different things. I mean, if you don't know, I can understand. If you don't remember, then that, I need to be worried. Okay. In that sense, you don't know, in the sense. Yeah, we have a WhatsApp group. You can do that. So one of those is, but it will be for one day. Okay, I'll give you one day, because it will not be indefinite, time. Yeah. Okay. So we will decide. Okay, right now you can go check and then try to put the message on this WhatsApp group. Yeah. So that Hardik will. Hardik is not on that WhatsApp group. So, but I'll inform him. Huh? He is it? Oh, okay. Okay. So I guess no, I'm not going to repeat this thing, and I'll give you all, put out that syllabus for your final exam. I'll add all the lecture slides as well as reference material, etc. Okay, and you can refer to it, and so on. So to make it easy, so I don't need to go through the technique for deriving. I went through the resolution method last time, right, to derive the conflict clauses. Yeah. Yeah. I don't need to go through it. Yeah. So the few items that were, so as I said, if you build the, just set the context, okay, so you can build this implication graph. Every cut of that thing represents. A cut means the sources thing. So if you take the conjunction and take the negation of it, that's a conflict clause that will block the conflict, okay, this particular conflict. And there are several of them. And we said that you can do get it with the UIP. The other approach is to, where did I? Yeah, is to do this, okay? Like use resolution inference, okay? I am.
Sir, can you share the screen?
Oh, I have not, is it? I'm sorry. Okay, I wished you had yelled at me earlier. So I put it somewhere down below. But then that's a different one. It's here. Okay. Oh, you should have yelled at me earlier, Sudakshina.
Sir, even now it is not visible.
Somewhere I did not do it. This is DPLL-T. Need to get to. Yeah, this is the one that tells you how to do it. So this you could do, you can do it as, you don't need to maintain the resolution, I mean, the entire implication graph. All you need to do is to maintain the list of literals that the BCP derives and the order in which you have considered them for derivation, okay? And then the final conflict, clause, and you can do, you can derive all the conflict clauses as illustrated in this example, okay, using binary inference rule. So you start with C2, which was the conflict clause, yeah, that gave, that resulted in the conflict. And then you use this, yeah, you consider all the literals that were implied literals, that were the literals that were implied at this level as a result of these decisions. Starting from C2, you resolve C2 and C1 on this variable, and that will give you one conflict clause. And you keep doing it, and then at each step, you will resolve the current thing that you have. Okay, you're starting here, and when you resolve, you'll get this. Okay, and then you take the antecedent of the next literal that you have derived in that order that I showed you, and you keep doing it, and you can keep on doing it, and every time you will be producing a new conflict clause through the sequence of things. And of course, in this case, since our goal was to generate a conflict clause that where the only literal, implied literal the literal implied or decision literal at the current level, there was a single literal, so that you could do by checking if it contains, when you encounter the unique implication point. Okay, so you keep on doing it until you derive a conflict clause in which the only literal at the current level, either implied or the decision literal, is exactly one. Okay, that'll happen when it contains a unique implication, a point like it happens in X4. It could be multiple ones, and the one that where all the literals in the conflict clause are the decision literals, always has that decision that triggered the BCP at the current level, the literal that was decided that triggered the BCP as the unique implication point. And that's when you will, so this procedure will always terminate because it is on, there's only finitely many literals that are implied by the BCP starting from the decision literals. And that's what this thing is. Yeah. Maybe this thing works. Yeah, it does. So that's what is shown here, and I will let you look at it. So this is all is done. So the few points on CDCL that I want to fill you in on. The other one is deciding the backtrack level. The strategy that is most wisely after you add the conflict clause, okay, with the unique implication, the first unique implication point, you could backtrack as before to the latest level, but what is usually done in most SAT solvers is to backtrack to the highest level. Other than, by highest, I mean in terms of the decision, the lowest number, okay? The highest level, other than the current level, I should be saying the lowest level if you count in terms of the level, because you're starting from 0, 1, 2, 3. So the highest level in the tree, in the decision tree, other than the current level, which created the conflict, okay? Yeah, this is because in practice, this turns out to be very effective. Because whenever you learn a new conflict clause, and if you undoing a lot of the work, and you're skipping over some satisfying instances that might be lurking around somewhere at the lower level, restarting it because it can prevent a lot you might have encountered. So, skipping the current level and backtracking to earlier levels, and this particular criteria seems to work better, okay, best in practice, and that is the reason. So, as I said, so that is the second highest decision level for any literal in C. So that is how you decide. Now, for example, for this conflict clause that has X1 and X4, okay? So other than this is the latest decision level. So the highest decision level other than the current decision level is 1. So you would backtrack to level 1. And since this is the only literal at the current level, so it will immediately block X4 from being 1, which was the reason for the conflict. Yeah. So whenever you have an asserting clause, by asserting clause I mean a conflict clause where the only literal at the current decision level is a unique, okay? So that has the effect of, as soon as you backtrack, it'll force you to make the right decision that prevents this particular conflict. And what I'm describing here is the backtracking level, that's all. So for example, if you chose this, which is also an asserting clause, because this is the only literal at the current level, your backtracking level would have been 2, because that's the highest level, whereas here it is making you to go to 1. Okay, so that is what is mostly used, and this is heuristics based. Okay, it's based on experiment and practice. They seem to get better performance, and that's the only reason. Okay, the other, I told you this learning, the non-chronological backtracking. So I'm going through the list of things that have contributed, in SAT solvers becoming quite efficient. The other one is your length of proof. Okay, how many decisions, very much. I mean, the number of levels that you have to search before you find a satisfying instance is very much dependent on the order in which you pick the variables to decide on. So earlier, so what criteria that that you would use? So the best criteria would be the one that can find you a satisfying instance with the lowest decision tree. Determining that means that you would have solved the original SAT solving problem. So there cannot be any efficient method to do it. So all techniques that are used in SAT solvers are some heuristics that seem to work in practice. Generally, what would you choose? If you were to choose, what literal would you choose to a variable? And there are two decisions you have to make. You have to choose the next variable to decide on, and whether you make it 1 or 0. Those are the two decisions that you have to make. What would you be your choice? Because you're trying to get a satisfying assignment, right? So you want to choose that variable that makes as many clauses simplified to true, correct? So then you will get, the idea is you have to choose that assignment to the variables that will make your entire formula to be true. And that may require multiple decisions. And therefore, you want to, at each time that you choose, whatever is left, the unresolved clauses at that time, you want to choose that variable that make as many clauses reduce to true. So you could do that, okay? So every time after a BCP, when you have to make a decision, that you could do that, okay? So some score you have to get. All these heuristics are based on some score that it keeps. So these are two methods that are used. So the DLS, which is D stands for the dynamic, I think, dynamic. And what is the dynamic? So you choose the literal that satisfies the most unresolved clauses. Okay. At any particular point, you have some set of clauses that are unresolved, right? So you have to make all the clauses go to true. So you choose that literal and that polarity. I mean, the literal, the variable, and the polarity that makes most number of things also. But this is, and you'll have to do this because if it is based on unresolved clauses, you'll have to do it every time. After each BCP, you will have to keep on recomputing this score, okay? And in order to figure out how many, that literal, how many times it appears in any of the clauses is kind of expensive. I mean, although because you will have to look through all the clauses to count the number of times, right? And therefore, it is expensive. So sometimes there is a static version. So you kind of do it once at the beginning by looking at all the clauses in your formula, and then don't redo it. Okay, that's another thing. But what seems to be the current standard practice, this is a static method, okay, in the sense that you don't need to keep computing. I mean, each time after you do the BCP. The other thing that this does is it's a static method, and also it keeps, CDCL keeps adding conflict clauses. Okay, you're adding clauses, and it takes into account the conflict clauses that are added as well. And let me just summarize this thing. So all this thing is in the book if you want to get supplementary material. So for each variable, you keep a counter, okay? Each variable, how many times that variable appears in positive form and negative form. How many times, in how many number of clauses it appears positively and negatively. That's what you keep. And that is computed once right at the beginning by looking at all the clauses in your input formula. And the only time that those counters are updated are, do I point? No, this is every time. I don't know. Sorry, I don't know how to, any of you know how to give the point here? No, it does. No. Okay, so I'll point out here. Yeah, but these counters are only updated not every time a BCP is done, okay? After a BCP is done, only after new clauses, conflict clauses are added. And you include, when you count the number of clauses, you also include the conflict clauses in addition to the original, thing. Okay, so that, that's what is done. And then periodically these counters are divided by some constant so that the number of the literals that appear more number of times in conflict clauses are given priority, okay? Because the rest remain the same. So as you go along, if you divide by, if you keep dividing it by some constant factor, the newer clauses, the conflict clauses, the literals that appear in the newer conflict clauses end up getting higher, higher scores, okay? And this is what is used. And this is, almost now a standard heuristics that is used to decide on the thing. So this gives a score. So in these counters, and what you choose is that literal whose this counter is the highest, so that it will make as many clauses disappear in your thing, including the conflict clauses. Is that clear? Yeah. So that's the one of the things that is done. Now, even here, there could be, so although this is not done as frequently as the dynamic method, it is done once at the beginning, once after every time a new conflict clause is added. Still the cost here is, okay, so anyway, so this decision, okay, so this is about the decision. The other engineering thing that is done, I mean, that drastically apparently improved. Okay, say the BCP forms almost 90% of the, generally the CDCL algorithm, where 90% of your effort is spent is in BCP, okay, the Boolean constraint propagation. As soon as you make the literal, you have to push through, substitute, and then you have to simplify all of them. 90% of the effort of that algorithm is spent there. So any effort that you put in to improve, any engineering effort to make that efficient would be quite valuable, okay? And what is, yeah, so inside the BCP, the most expensive, expensive thing to check would be when it becomes unit, okay? Is it not? Because the moment it becomes unit, that forces an implied decision, which then has to be plugged up. So you will have to, after each decision, you will have to, after simplification, you will have to determine which of the clauses becomes a unit. So one obvious way, once again, is to keep a counter for every clause that gives the number of literals set to 0. But this requires you to visit the clauses every time that it simplifies. You have to keep visiting all the remaining clauses to keep computing if things, you have to visit those clauses to see if they've become unit or not. So here we are talking about tens of millions of clauses, formulas that contain tens of millions of clauses. So, but this is, while this could be it's a very clever technique, and that's why I want to bring this to your attention. And, so, although this is kind of quadratic, I mean, linear in the number of clauses and the frequency with which you will have to keep doing, and with millions of clauses, tens of millions of clauses, takes a lot of time. And therefore it can be, there is a techniques that can be where this checking if a particular clause becomes unit or not can be done in constant time, okay? In constant time, that is independent of the number of clauses. And that's why this was kind of a patented, a method that got patented and is used in almost all present-day SAT solvers. And what it does is it can be done by keeping for each clause two what are called watch literals. In each clause, you only watch two literals, okay? And visit the clause only when one of its watch literals is assigned to 0, okay? Because if you have two literals that you're watching in each, so the only time it can become a unit clause is when one of the, both of them will have to it becomes 0. No? So you, every time that you make a decision on a literal, you just need to see if there is any clause whose watched literal, the number of watched literal becomes 0. So that's, otherwise it is not implied. So only when you make a decision on one of the watch literals, do you have to go visit that particular clause. And then if one of them has become, if one of the watch literals is what you made the decision on, then you pick another, if there is one in that clause, and replace that with the new watched literal. Okay, and that's, when there are no more literals, then you know that it becomes unit. Okay, therefore this business of where you keep the counter and then you will have to keep modifying the counter is not there. So this is another. Is it clear? So you will have to give two things, and then you will have to go to that only if one of the watched literal, the current decision that you make is one of those watched literals. You only need to visit those clauses whose, which matches with, whose watched literal matches with your current decision literal. So, and another thing is that this never changes. Okay, whereas the counters, you will have to keep resetting when you do backtracking, etc. Whereas here, that does not change at all. The watch literals change only when you make certain decisions. Okay, so that is, some of the points that I wanted to make. Okay, so let me go back to another thing. Okay, which I skipped. Oh, there's some questions here. Dakshina, can you hear me now?
Yes, I can hear you.
Oh, okay. So that was an earlier thing. What happened? Don't forget it. Okay, so I had these. No. Okay, so there was this, yeah, let me, the remaining time that I will spend, I mean, there's one thing that I skipped, since I don't have the slides here. I don't know, rather than spend the time. This was to address this encoding, okay, you see that there is, because that's always require their input formula to be in CNF. And I told you that to get any arbitrary formula that have other Boolean functions, they're used into CNF formula, that itself can have a blow up, okay? There is an encoding mechanism called Cyton encoding. I will refer you to the, and I had the slides in one of the lecture slides. I will point you to the reference. There is a special kind of encoding of where you can get the formulas in CNF form without encountering an exponential blow-up, which happens because of distributivity and De Morgan laws, okay, that you will have to apply. And that method is kind of a decomposed methods. There are a few slides. It's fairly easy to follow. You just look through, and I'll give you a reference for that, okay? By introducing new additional variables, which are only, a linear number of additional variables, it avoids an exponential blow up in the number of clauses. It does increase the number of variables, but it does not, it does not cause an exponential blow up in the number of clauses, okay? So, since I don't have the slide here, I'm going to skip that. And I'm going to, in the remaining time, just give you an idea of this thing I'll spend the time on. So remember that I had introduced offline algorithm long time back, okay? Do you remember, that? So where, okay, I'll get to the clause, okay, an example to remind you of that thing. And what I'll be describing today is certain improvements to this, to this thing. So what we talked about today was DPLL. I mean, so far was DPLL, okay? Then the CDCL version of it, which was able to do propositional solving. What we are interested in is extending that to formulas where the first order formulas, where the atomic formulas are drawn from some theory. And the theory of interest for us with the DNN is linear arithmetic. Okay, so that's what this is an example of. And one naive way of doing it, I had illustrated, is first to get a Boolean abstraction of it. Okay. And then, so whereby you replace, so you ignore, I mean, any satisfying instance of this has to be, it has to satisfy the Boolean structure, as well as it has to satisfy the theory constraints. So in this case, is this satisfiable? Anyone? It is. Huh? Because in order to satisfy this, we'll have to make x is equal to 1. And in order to satisfy this, we have to make x equal to 2. Okay? So this is not satisfiable. Although when you take the Boolean abstraction, this Boolean abstraction is throwing away some information. So this is satisfiable. So, the idea, whether it's in DPLL-T, is first get the Boolean abstraction, get a satisfying instance, and then you check if that satisfies the theory constraints, okay? And then once you get a satisfying instance, for example, B1 and B3 is a satisfying instance, then you check. Then you get the actual concrete version of it by applying the inverse of this abstraction, and then you check, okay, for which you can use an LP solver. If you have some other theory, you use a theory solver, okay? And that's the idea. So decompose it into two problems, because the theory solver is only able to solve conjunctive fragment. So you use the CDCL method to get a satisfying instance of the Boolean abstraction, and then you do it, okay? Now, what is the disadvantage of this? Okay, so the soundness, this I've discussed, I'm gonna skip this. So in this case, for example, you will have to, okay, so, you know, the first try, you have to almost, I mean, in this case, you have to enumerate, since you're producing, you know, full satisfying instance. So you will end up enumerating all instances. And then before you do, once you do this, you see, I'm blocking the previous instance by doing the negation. I mean, taking the negation of that. And then I will get things. In this case, because it's unsat, you will go through the entire, I mean, all the possible instantiations for the variables, and then you do and you do it. So that is the thing. So the question is, this will not scale at all. Okay, this offline algorithm. That's why I call it the naive algorithm. What can you do? So the idea is you will have to somehow, you cannot be considering one satisfying instance at a time to check the thing. So first is you have to somehow reduce from the number of instantiations that you consider. Now I want to show this. Okay, so each of these things causes a theory conflict. This is at the Boolean level, it is very well a satisfying instance. The conflict it comes from is the theory. That's why this instantiation is what I call is causing a theory conflict. Theory conflict, you understand, yeah? So what you can do is, instead of one way, and since we have discussed about unsat core, I just want to show this is one way, but this is not how real DPLL-T in an SMT solver works. That I will get to, okay? But here, this is one way to consider, instead of, you know, avoid enumerating all possible instantiations. So for example, here you know that this is a unsat on the theory, okay? You could get an unsat core. So this is like a conjunction of bunch of clauses, okay? So in order for this, see, any pair of clauses, I mean, literals here makes that unsat, right? So you could take the unsat core, if you remember, the definition was that it is the minimal number of clauses that make a particular formula to become false. When it is an unsat formula, it becomes false, of course. So you could take the unsat core, which means that, you know, so you take the unsat core of that thing, so any pair, and then you could, is this the correct one or? Correct, okay. So what I've done here is, after this, I'm taking the unsat core. So B1, B2, or B3. No, yeah, not of B1. Instead of just, you know, analyzing one at a time, I'm taking not B1 or not of B2, okay? So the unsat core, even this subset makes it false. So that I can use that, the negation of that, and then take it. So that way you're doing, you know, making it simultaneously, okay? But still, you will have to, so it reduces from the 8 different instantiations to consider. It will make it, a fewer number of instances to consider. But what is happening here is that, this is one way. I showed you as an illustration on set core, but the core problem here is you're not putting the partial assignments to good use, okay? The moment you made B1 to be true, okay? So B1 has to be true here, okay? The only choice you have is B1, B2, both of them became false, make them, either B2 or B3, either way, it will make them false. And that's why B1 and B2 itself causes a theory conflict. So does B1 and B3, correct? And therefore, instead of choosing one little at a time, I've chose an unsat code that made this thing. But what is really the problem is you could, as you make your decisions on the literals, you take the partial assignment, okay? Instead of calling the theory solver after the entire assignment, full assignment is made, why not, that's what, invoke the T-solvers eagerly to see if the partial assignment that you made already conflicts, okay? So of course you make a decision on B1, then you make a decision on B2. You can call immediately after that, although that is not in this case that happens to be, instead of waiting to get a full complete assignment, after every partial assignment, you can invoke the T-solver. Now, if on that partial assignment, if your T-solver says, oh, no, this cannot, there is a conflict, then you don't need to consider any further assignments, any extensions to that partial assignment at all. So a whole exponential number of, search part, really of the search tree is eliminated. And that is one idea. So that is one. So you invoke the T-solver eagerly after each partial assignments. The other thing is integrating into CDCL framework. What is the advantage of CDCL? Conflict-driven conflict learning. So every time you got a conflict, it learned something. So you could do the same thing. So there was no learning in this offline algorithm that I was using, okay? So you could, if you integrated into the CDCL framework, so here the CDCL was being called as a black box, okay, that's all, yeah? So the idea is to more tightly integrate the, this process as you kind of integrate the invocation of the theory solver into the CDCL process itself. And that's what the DPLL-T does. Okay, so I'm going to give you just an overview. I only have half an hour. Okay, and please let me know. So I just want to have you get an idea. So you follow the, even if you don't follow all the intricacies, follow the example. Okay, that I will show you, and hopefully you should. You will understand. Okay, this is the online version of DPLL-T. Okay, now the structure here, forget about the first part in here. There is some pre-processing part that ignore this. Okay, start with your original formula. The original formula is phi. Okay, and this is the propositional structure, the propositional abstraction, where you replace every atomic formula by a unique propositional variable. That's what phi p is. Mu p, you start with empty, yeah? And your CDCL, this is exactly the structure of CDCL. You make a decision, yeah? And And you, so in the standard CDCL, this would be just the decide, okay? Whereas here there is a slight variation of that decide procedure, which is what I call as T-decide. And then you T-deduce. This in the original CDCL was just BCP, okay? Whereas here, yeah, okay. No, I'll skip this. Okay, so I'm talking about DC, yeah. So select an unassigned variable and you decide whether to make it true or false, and then you add it to the current partial assignment, okay? Yeah, so in this case, T-deduce invokes BCP and the T-solver, okay? In the earlier offline version, you were just, since CDCL was just a black box, you had to get the entire satisfying assignment before you do it. Whereas here, as soon as you do, BCP, you also invoke T-solver to check if the partial assignment is okay with the thing. And that's what this thing is doing. So the T-deduce will take phi p, mu p, and then applies BCP. If mu p, the current assignment, violates phi p, then that is not the assignment that you want, correct? Okay, so then you have got a conflict, and then you do whatever CDCL does to find a new assignment to it. But let's suppose that you eventually get to a thing that satisfies phi p, okay? That is the current partial assignment. When you plug it in, all the clauses are reduced to true, yeah? Then you have to invoke T-solver on the concrete version of it, yeah? So if that gives SAT, you're done. Otherwise, there is a theory conflict here, right? This assignment is not, is not satisfying the theory constraints. So that's when, yeah. So then there could be a conflict. Even then, you will have to go to the analyze conflict, to how you will analyze the conflict as you were doing before. Otherwise, I mean, even in the case where the partial assignment would have not reduced it to true, but rather it has some unresolved clauses, you still call the theory solver on it, okay? And so that's when no more literals to be deduced at this point. Invokes T-solver on the partial assignment of the thing, and returns, if that returns conflict, you return unsat. Otherwise, you can do lots of things. With the partial assignment, you can. That is the other case, is when you have not reduced to true, but then there's no conflict. That is the case when you have some unresolved clauses still left. Even then, you call the theory solver. And you can do two things. You can derive certain true facts about the current set of theory literal that you have, that the partial assignments have assumed, and then you can add them. So you can learn new theory consequences of it. And of course, if that is unsaid, then of course, you don't have that, and you will have to consider a different assignment. So that is the idea here. So if there's a conflict, then which could be either, if it is only a Boolean conflict, then you handle it in the CDCL way. Otherwise, you will have to, so this has to take into account, this analyze conflict is also will be extended slightly to take into account how you resolve the conflict that you got as a result of theory violations. Okay, and that is what I will show you here. Okay, and just like before in CDCL, this also gives a backtrack level. It gives a conflict clause to add, and you will see there are multiple kinds of conflict clauses that you can get. And the new set of kind of conflict clauses are something to block the theory conflicts in the future. Okay, so that's what is happening. So analogous to CDCL, there's a backtrack level that it gives. Okay, let me quickly get to an example. Okay, so that's enough of generality. So you can go back and then you can look at that. Okay, so here is my, these are the formulas, and the blue ones are the propositional abstraction of it. So the atomic things are, I mean, I've also added a few Boolean variables which are in the mix there. There are some atomic formulas which are purely propositional variables. Some are drawn from linear integer arithmetic. So each of these atomic formula from the theory is replaced by a Boolean variable. Okay, that's all I've done. The blue is clear. Yeah. So now let's start. So I'll have to make these set of decisions, okay, before any BCP can happen, okay? So start with level 1, where I make, yeah, B5 to be false, okay? And as you can see, so this will go away. Not of B5 is true, so this whole thing will go away, okay, and so on, yeah? And B1, and you can believe me that any of these things will not simplify, you know, give rise to any further, does not make any clause unit, okay? So now, once you make this, so this is gone due to this is gone due to this, correct? And B6 is 1. This is gone due to this. Clause 6 is gone. And B8 is 1. Where is B8? And this is also gone. Okay, but there's still, there are a few that are left. Now, the first thing is, so in this case, in the normal CDCL, what would have happened now? If you were only doing the thing, you would make a further decision, correct? But here, due to these two decisions, you see, these are Boolean abstraction of linear, atomic formulas from linear arithmetic, okay? So I've shown here, above, here in the note, what not of B5 is. B5 is this formula. So not of B5 is, I'm sorry, this one, okay. No, forget about this, okay? This is a new clause. This was not in the original one. So B5, yeah, this is correct. So this is B5. This is B5. What I've shown is not B5, okay? So these two in the theory infer not of B3, okay? So this is what is called theory propagation as, okay, in addition to checking if there is a conflict as a result of the decision. So here there is no conflict, okay? But you can use the theory solver. That's what I meant. You can use the theory solver to infer new formula. As a result of making these two decisions, does the theory of linear arithmetic imply or infer, make some of the other literals, other atomic formula here go to either true or false, right? Because that, you know, if you can have T solvers, linear LP solvers can do that. I mean, of course, there are so many facts that you can derive, but not to worry, because you only are interested in those atomic formulas, atomic linear arithmetic inequality in this original formula. And that's why, so you can do that search. So the first thing is, this is theory propagation. As a result of any of these partial decisions, you will see if it either, you invoke a T solver to see if it creates a conflict. If so, then you will have to back up, and look for a thing. In this, look for a different assignment. But in this case, even you can do some theory propagation, which you would not have done if by traditional propositional CDCL. Is that clear? Yeah. So I'm using the T-solver for two things. One is to check if my partial assignment to any of the linear arithmetic atomic formula creates a theory conflict. The other thing I'm doing is see if, even when it does not cause a conflict, if it infers, if it makes any one of the literals in here go to become true or false. In this case, not of B3. B3 actually happens to be so, and that the reason I have described here. Okay, I've just taken B5 and B1, a negation of B5 and negation of B1, kind of moved around the the variables, and these are the two things. Okay, the B5 and B1 after moving around, and as you can see, as a result of these things, the minimum value of 3x1 minus 2x2, which is what B3 is. Okay, B3 is 3x1 minus 2x2. The minimum value has to be 4, okay? The minimum value has to be 4, whereas this one is requiring that it has to be less than or equal to 3, okay? Therefore, it is deriving, not of B3. So I can add this, yeah? And now I can get more things to simplify using BCP, yeah? So this is the tight integration that I'm talking about. Yeah, that is the advantage that you get by invoking T-solver eagerly, even before you find with a partial assignment. Yeah. So now, yeah, because I call it early pruning, because anything new that you derive, will cause more simplification, and more of your thing is simplified, and then it helps you that way. So, yeah, that's thing. So then your BCP kicks in, yeah, as a result of theory propagation, yeah. So not of B3 makes in C5, it makes A1 unit. And that inside C3 makes a C3 unit, and it implies A2. This is all due to BCP, not due to theory propagation, okay? And that creates this, a conflict, okay? This is, okay, oh, by the way, I missed one thing, okay? As soon as you derive a new theory literal as an inference, you can also add that as it's not a conflict clause, but it is some new thing that you have learned from doing theory propagation, because this is actually a fact, okay? That you can actually use, because if B5 and B1, if not of B5 and not of B1 is true, then it follows that not of B3 is true. So because that is something that you add, which is not a consequence of your Boolean abstracted formula, but it was a consequence of your original concrete, okay, formula, because it is sound to add that also, yeah, so that later you could use that in your search process. And that is what this is not a conflict clause, because it is not produced by conflict clause, but it was something that was inferred to theory propagation. And that's what this thing is, okay? And then you do all these things. Now there is a real conflict, okay? So just like if there was conflicts, there are two kinds of conflicts that you can have due to some purely Boolean decisions that were made, okay? Boolean decisions that were made. Then you will handle that as CDCL would have handled, and that would produce what I call as a pure Boolean conflict clauses, yeah? But here, this particular conflict is what I call as mixed Boolean theory conflict. Why? As the name suggests, in the interest of time, tell you, because it's as a result. And that is true, but why it is mixed Boolean theory? Because this conflict is depend on a certain theory fact, okay? It is not purely on thing, because see, this conflict is dependent on not of B3, which is as a consequence of this only at the theory level, not purely due to the decisions that you have made, okay? So for example, if you have made these two decisions and if you had some other, Boolean fact that was being inferred, then it would have been a purely Boolean thing, because this is a conflict that is being caused due to certain Boolean decisions you have made, like you said, as well as certain theory facts that you inferred, okay, as a result of those Boolean decisions. And this not of B3 was one such thing. Yeah, was one such thing. Yeah, here that is the only one, but theory propagation can cause as many literals to be inferred in your thing as you make more Boolean decisions. Is that clear? So that's why this one is called mixed Boolean theory conflict. Okay, and this is handled the usual way only. Okay, so you will analyze this implication graph, and this happens to be a unique implication point, and therefore this one is a conflict clause as produced by the analysis of the implication graph or through the resolution graph, resolution that you did. Yeah, and that's the the two important differences. Okay, so as I said, there are two kinds of clauses that are added here. Okay, once again, I want to re-emphasize. One is, it is these kinds of clauses like 8, okay, clause 8, which were added not due to conflicts, but due to theory propagation. Okay, so they were just happened to be inferred by the theory of linear arithmetic. Okay, they followed as a result of this. The other thing is due to conflicts. Okay, here I showed you one mixed Boolean theory conflict. Of course, you could have only Boolean conflicts as well. Yeah, so that's so of course there are two things. I mean, you could add just this and you could be satisfied, and this is an asserting clause, okay, because it has a unique implication point, because as soon as you add here, and then you would chronologically backtrack to the highest level of the other literal, which is B8 here, 2, because B6 doesn't appear in here, so you would backtrack to B2, correct? Highest, you look at all the literals here, other than the current, literal at the current level, the highest, level for the is B8, okay? Because that's, 2. So you would backtrack to 2. As soon as you backtrack to level 2, what will happen is, because you keep these decisions, and this will flip a B2 itself, B2. Now, of course, as I said, here you can add more. I mean, you can add all other conflict clauses that have other UIPs as well. In this case, that happens to be the one that you get by going all the way back to the sources. There's no need to add that. Okay, here I've shown as though that is to be added, just to illustrate that if you add it, you will see that this B1 immediately is implied by BCP. But even without adding it, if you just added this, you will see that there's a chain, and therefore it will prevent you from making B1 to be 0, 0 again. Okay, so that's what I'm this note I'm having. I'm asking the question: is it necessary to add the second mixed theory conflict clause to flip the decision on B1? No. Okay, but as I said, I mean, there are various other methods. Some people add all the clauses, which will have a blow up on the number of conflict clauses, or some people add all the conflict clauses that have that are asserting, in the sense, an asserting clause is one in which has a UIP, okay, at the current level. There could be multiple of those things. That can also be added. So that's what this thing does. Okay, so the two main. Once again, I want to emphasize, this is kind of the last slide that I have. I'm going to end at 6:30. I'm not going to go beyond that. So I'll see if I can find the other slide in which I've cited. Otherwise, I will just give you the thing. So two important things. One is, this is a closer integration. Online algorithm, it differs from offline in that it closely integrates, okay, it into the CDCL framework. As a result of that closer integration, what you get is you keep, whereas the earlier offline method called CDCL algorithm, the Boolean thing, as a black box after getting the full satisfying assignment to check the whether it met the theory constraints. Here you call T-solver after, more frequently, after each time that you make a decision, okay, and then you do it. And that you can use that in two ways. One is not only to check if the current partial assignment has a conflict. If it does, then you will generate a conflict clause, a mixed theory, a Boolean theory conflict clause. You add, and then you do backtrack, and then you try for another assignment. Yeah. But that has early pruning because it prunes away a lot of the portion of your search space that is not going to be productive as a result of inference of theory. Even when there is no theory conflict, the T-solver can produce a new facts about the thing. That is another kind of conflict clause that you add, and that's how you do. That's how it works. So that's why I made the note saying it is putting each partial assignment to good use, okay, in learning about the partial assignment with the help of the theory solver. Okay, so that's where I want to end. Okay, yeah, so this just shows, okay, there is even tighter integration. Okay, so here, see, in offline there is just, it just gives sat unsat. Okay, whereas here it is more the tighter integration within CDCL. And so there is the T decide, the T deduce is where a lot of the work is going on. It does BCP as well as T solving. Okay, so let's see if there are any other. No. Okay. This is where I end. Any questions about DPLL-T or any logistics, programmatic, questions on assignments, the final exam and so on, or is it all okay? So then, thank you for taking the course. I hope you enjoyed it, and best wishes and best luck for all your future endeavors. Okay, thank you. Yeah, you guys. Yeah. So tentatively, I'm going to send an email. So you will check. Okay, tentatively, we agreed on you all will be back home to take the exam December 2nd. Okay, correct? So if I put it on December 2nd, it is due on December 3rd. Okay, if indeed you're traveling on 2nd, then I will push it by another day, which I will announce. Right now, the tentative date is December 2nd. And the final presentation is on December 12th. Yeah. I'm thinking 24 hours, but if I have, if I think that you need 48 hours, then I can, based on, I haven't made the exam yet. So if I feel like it's kind of difficult, it's 48, I can make it 48 hours. Yeah. Yeah. See, the longer I make, the longer I give you, the closer it gets to an assignment, okay, as opposed to kind of an exam. That's all I'm doing. So I prefer to keep it 24 hours, and I can make it 28 hours, yeah, and 48 hours. Okay, good. Yeah, I think you should get the grade on the second assignment in a couple of days, okay, and we already started grading it, and so we'll have some idea of what the where you stand on your thing. Yeah. Okay. Yeah, I mean, of course, any doubts that you have, Diganta couldn't be here today, but nonetheless, you get started. See, we want to get an idea on the experiments. I'll tell you why, because the effectiveness of the that whole thing will very much depends on how good the criteria is, and that is what the thing is. The sooner you get some feedback on what the experiments is, the better that we'll feel about this whole method. Okay, and we're also saying if we get good results in the experiments, then it makes our case for submission to that SMT SAT better. Otherwise, I mean, more confident that we can do. So, I appreciate if you can give feedback on that. And any questions now that the WhatsApp group is there, you can feel free to ping on that group, and we'll all be on that. Give you feedback. Yeah.